Hi everybody, RH here. I want to give you a clear introduction to ordinary differential equations. I know many of you are taking a course right now and trying to figure out what you're actually doing and why you're doing it. My goal is to give you the background behind differential equations so you can see the big picture. At the core, differential equations is really just about rates of change. It's all about differentiation, hence the name, differential equations. In many physics situations, we don't start out knowing the underlying function that describes what's happening. What we actually measure or observe first is a rate of change. Let's take a look at some examples. So here I have several examples. We're going to start with the Apple Watch. An Apple Watch has no means of measuring orientation. In fact, what the Apple Watch actually measures is a rate. It measures the rate of change of angle with respect to time. It's that rate which is then converted into an angle which gives orientation for the watch. Our next example has to do with heating and cooling. Anytime that we have an object like a cup of coffee, which is not the same temperature as its surroundings, whether it's hot or cold, then what we have is a rate of change of temperature. We don't know the actual temperature function. What we do know is the rate of change. And it's that rate of change that we can use to help us describe what the actual temperature is at any given time. The next example has to do with a basic disease model. We track three states of the situation in this particular problem. The number of people who are susceptible to a disease, the number who are infected, and the number who are recovered. And what that gives us then is actually three dependent variables. So we have the rate of change of the number of people who are susceptible, infected, and recovered. And this is called a system of differential equations. And the way in which we handle this is similar to other types of differential equations, where we use the rate information to come up with the model that is going to give us predictions as to how many people will get sick, when is the peak infection going to occur, and what does the recovery look like for people. Another example is with medicine. When you take medicine, your body absorbs it at a specific rate. We don't have a function a priori that represents the amount of medication in your body. What we have instead is a rate of change of medicine with respect to time. And this is a function of absorption rate and then elimination rate from your body. We can derive, and this is important for doctors and nurses knowing what medications they can prescribe, when they should be taken, and when they should be refilled. So this information is important, and it's all based upon rate information. The last example I have are the SpaceX rocket boosters. In order to put the boosters back on the ground, we need to have velocity approaching zero, except the boosters don't have velocity sensors. What they have are accelerometers. And what we know is that acceleration is the rate of change of velocity, and that information is used in order to calculate the velocity of the boosters so that they can be landed and not crash into the ground. These are just a few examples of the myriad of science and engineering problems where rate of change information is available. Studying ordinary differential equations is the key to extracting the underlying functions from the rate equations. What I want to do now is just take a little bit of a deeper look at this example. In this situation, we have a cup of coffee. And we're going to define capital T to be the temperature of the coffee and lowercase t to be the time since we first poured our cup of coffee, and then T sub S, which is the temperature of the surroundings. What we're going to do is take a look at how we understand what the temperature is going to be as a function of time. That's the function that we're interested in finding. Well, we don't know what the temperature is, but we do know because of Newton what the rate of change of temperature is. We understand the rate of change of temperature with respect to time. Newton, over 300 years ago, understood that the rate of change of temperature is proportional to the temperature difference. So it's proportional to the temperature difference between the object, which is for us T, and then the surroundings. And what we're going to do then is turn this into an equation. Our equation states that the rate of change of temperature with respect to time is proportional to, so we're going to multiply by a proportionality constant, the temperature difference between the object, which is T, and the surroundings. And then we're going to choose K to be a positive number. At this point, we need to stop and think about our model. And remember, differential equations is all about modeling real life, and so what we're going to do is evaluate what this means. When we have a cup of coffee, the temperature T is larger than the surrounding temperature. So this is a positive value. And then we also know that K is a positive value, and when we take the product of two positive values, that's of course going to be positive. But then think about what our equation would say. It would say that the rate of change of temperature is positive when the coffee is hot. In other words, the coffee is going to continue to get hotter as it sits out in the room. That's not what really happens. And so in order to make this model accurate, we actually need to put in a negative sign. And we have the rate of change of temperature with respect to time is negative kT minus T. This is Newton's law of cooling. This is a differential equation. This is an equation that relates a rate, which is the rate of change of temperature, to the function t. And what we do then is we solve this in order to come up with what the function is. So, whenever we're learning a new mathematical subject, it's not enough for us to just master the skills. We really want to understand the concepts. It helps us to better perform and remember what's going on. So stay tuned for future videos, and if there's anything I can do to help you out, just let me know. Thanks.